Hey guys, it's Mr. Sheeline here. This is the video for the 4.3 notes covering acceleration and motion. So let's just jump right to it. So here are the student learning objectives that I hope you guys are able to fulfill. Excuse me. For this section in this unit 4. I can understand that acceleration can happen positively and negatively. So that's something that we looked at specifically already in the velocity time graphs. So it's just to say that, acceleration is, I want you to understand that acceleration is not just increasing velocity. It is also technically decreasing in velocity as well. It's just typically uh, we use the term acceleration pretty much in everyday life. We use it to talk about how someone increases speed of something rather than just the change in it. Okay. So I want you to be able to understand that. I also want you to be able to identify acceleration, velocity, and displacement as vector quantities. So all three of these guys are vector quantities. So I want you to be able to know, and for later on when we get to the test, to be able to say, oh, acceleration is a vector quantity, velocity is a vector quantity, displacement's a vector quantity. Okay. And then finally, I want you to be able to calculate acceleration when given time, final velocity, and initial velocity. So we'll be getting to what those are here in a little bit. Hopefully it's pretty, I guess, self-explanatory what they are, but we'll get to that in just a second. Okay, so just another reminder, we're still working with one-dimensional motion. So we're still just working, we're still just working with motion that's found on the x-axis or just on the y-axis. It's only a straight line. So that's all that we're working with here. And it's still, as far as one-dimensional motion is concerned, we're still, for the most part, we're just going to be working with, most of it's going to be uniform motion. I guess uniform motion in the idea that it's going to, we'll have constant acceleration. I know it says constant speed there. We'll say constant acceleration because obviously constant speed would mean that there is no acceleration. But there may be a question or two where you're riding along increasing velocity and then you're decreasing velocity and then you're increasing again. I may have some questions about that for you. So, okay. Now, what is acceleration? And I just realized I am now showing you guys the student version of these notes. So I'm going to pause my recording and I'm going to pull up the actual ones. All right, so we got that situated. Sorry about that. So acceleration is the rate of change of your velocity. Okay, and again, because we're using velocity, that means that direction matters. And if direction matters, that means that we have a vector quantity here. So we treat acceleration as a vector quantity because it is a vector quantity. And just here's another reminder. This is what a vector quantity is, which we should have this drilled into our brains by now. It is a quantity in which we care about direction and also the magnitude. Okay. So we care about how big the number is or how small the number is and which way it's moving. Okay. Now, to calculate acceleration, we need three things. So speed and velocity, we only needed two things. Acceleration needs three things. So we have what's called the final velocity. And final velocity is just velocity. We'll get to what that is in a second. But it's velocity measured in meters per second. In this case, we're really not going to be working with kilometers per hour. We're just going to be working with meters per second. Just make it easy on us. And then initial velocity, which is also measured in meters per second. And then time. Okay, so we are working with things that we've worked before. We're now just changing them a little bit. So here are the symbols that we use for all three of these. So final velocity, we use V and then like sub F. Okay, so that's a subscript F. Okay, so final velocity, easy peasy. Initial velocity, it's just V with sub I. So there's just a lowercase I as a subscript. And it should be fairly obvious, it should be fairly obvious. We have initial. Initial velocity, we have an I. We have final velocity, we have an F. Okay, so that should be fairly obvious here. Okay, and then we have time. Okay, and time's still just t. Okay. Now we still use brackets, same as we did with velocity and displacement. We still still want to mark the direction. My goodness, I keep yawning. Sorry about that. When we are detailing the direction that these things are moving, we still use them with acceleration. What does change here, and this is why I'm kind of blazing through this, is because really this is, it's the calculations that really matter here. And I'll show you a quick little visual, or no, because you'll be doing that on your assignment the next day or two. So what really changes are the units, and I know that this spooks a lot of you guys out, or at least it did in the past. And I know it did a little bit for a couple of students that did. I worked with earlier this year with acceleration. So the units are kind of different, and I want to break down the units after we look at the formula here. So because the units do make a difference insofar that you could easily confuse the units for some sort of mathematical operation when they're just units. So here's the formula. Here we've just have A for acceleration, which I forgot to put that in. This is the symbol for acceleration here. It's just A with an arrow over top of it. Okay, so not too different from velocity. Okay, so but we've got acceleration here. Okay, so just A with an arrow. Acceleration is equal to the final velocity minus the initial velocity divided by time. Okay, so think of it in this way. So order of operations would tell you to do this. You're first going to subtract the initial velocity from the final velocity. Then you're going to divide by time, and you'll have your acceleration, which makes sense because what you're saying here is oh my goodness, come on, eraser. What you're saying here is that you're saying that, well, this is the final velocity that I got, meaning that is the velocity that I measured at the end of my measurement. Here is the velocity that we started with. What's the difference between the two? What's the difference between them? So then once you find the difference between, your starting velocity and your ending velocity, the difference between them, how much time overlap, or what was the time interval? How much time passed when you went from a particular velocity to another? Okay, which makes sense. I mean, that's pretty much we're measuring it's measuring the change in velocity. Now, the units for acceleration are a bit strange, like I mentioned. So we're going to be looking at the formula here again, but we're going to be looking at the formula and we're going to swap out the symbols for the units. So here, velocity, obviously, velocity's got meters per second. Time is just seconds. So let's take a look at this. Okay, let's take a look. So here we're going to go from left to right here. So here's what we started with. We've already seen this. This is this is the formula for acceleration. So this is what we start with all the symbols. Then we're going to go over here. And here now we've swapped everything out with the units. So we have meters per second minus meters per second divided by time. Okay, which then that goes down to here. And then this is what we'd be left with. We'd still have meters per second on top, but then we've got to figure out what to do here. Now we've got seconds, like we've got a fraction up top and then a fraction below the other fraction. So what do we do? What kind of units do we use here for acceleration? So what the general rule is that when you have a fraction in the numerator like this, okay, what you do or what happens and what this is actually saying is that this guy right here, the denominator of this first fraction here, is actually down here, and you're going to multiply it by whatever's down here, which in this case is seconds. So that means that the units that acceleration uses, the units are this. They are meters per second squared. Okay, those are the units that we're going to be using here. Okay, so again, acceleration uses these units right here. Meters divided by seconds squared. So remember, just real quick, when you square something, it's literally just it's nothing but multiplying a particular number by itself. In this case, it's a particular unit by itself. So like it'd be like this. So what's the square root of 2? Well, it's 4. Okay, because it's the square, or sorry, not the square root, but 2 squared, sorry, is equal to 4. Because all it is 2 times 2 is, and that equals 4 here. Okay, these two things are the same idea right here. Okay, or if you want to say 4 squared, okay, 4 squared would just be 4 times 4. Okay, it's 4 times itself, which is 16. Okay, if you had 3 squared, that's the same as 3 times 3. Okay, so that's what that square is on the units there. Okay, so I'll draw that again. So the units are meters. Oh my goodness. My God blessing stylus. Come on. It's meters per second squared. Okay, those are the units we use for acceleration. That squared, this 2 right here, it's an exponent that just sticks with seconds. You don't use that at all in your mathematical equations. It's just the representation of the unit. So please do not get this confused in any of your calculations. And we'll go through those calculations in the Check Your Understandings. Okay, but do not get those confused. Okay, do not. Okay, so let's keep on moving. So it's important to remember that the seconds squared, so the S2, okay, doesn't affect any of the numbers you work with when calculating acceleration. Okay, so here are the equations though, just like I've been doing. Here are the equations. I gave you the acceleration equation, but here I broke down, if you, let's say you need to find final velocity, here's the derivation of the acceleration equation that you would use. If you need initial velocity, here is the equation to find initial velocity. If you need to find time, here is the derivation in order to find time. Okay, because there will be problems where you're going to be given acceleration, final velocity, and initial velocity, and you need to find how much time has passed in during that scenario. And then one last thing to make a note of, and this is something that you've got to be careful of. So we'll be working with a lot of problems that talk about starting where something started from rest. So when we talk about and measure acceleration, when something explicitly or a scenario is very specific about a particular phenomenon. So a good example would be before you fire a firearm. Clearly we're starting from rest, meaning our initial velocity is 0. Or it'll explicitly say, the problem will explicitly say, the car was at rest. The runner started from rest. Okay, and what that's saying is that the initial velocity is 0 meters per second. So keep an eye out for that. And that's where, laying out what you have, what you don't have, all your variables and all of their particular values, it's invaluable here. Okay. And then also draw some pictures. If you don't know what's happening in a scenario, draw a picture. Okay. I can't stress this enough to you guys that I've mentioned before, something I stress heavily to my physics kids. So let's just jump right to the Check Your Understandings. There should be about 5 of them. Let's see if I remember correctly. Yeah, 5. So let's just go through these. Remember, I want you to do these on your own. So I'm going to read these out. Pause the video, solve this for yourself, and then hit play to see if you get this right. Okay, so I'm going to read it out. So a resting car takes off suddenly and reaches 60 meters per second in 6 seconds. Calculate acceleration. So pause the video here. Try this out on your own. Okay. So here's what we should have done. So again, we should be writing down what we know and what we don't know. So a resting car takes off suddenly and reaches this velocity in 6 seconds. Okay, so, and I'm told to calculate acceleration. So this tells me that initially, this car being at rest had an initial velocity of 0 meters per second, and it reaches 60 meters per second. So that's my final velocity. Oh my goodness. And then it did it all in 6 seconds. And I'm trying to calculate what my acceleration is here. Okay. So I've got my initial velocity, I've got my final velocity, I've got my time, and I'm trying to find acceleration. So now I'm going to write the formula. My stylus will let me. So it's going to be the final velocity minus the initial velocity. Oh my goodness. I might just do this on a piece of paper. My goodness. This is absolutely ridiculous. Okay. So there's my equation, roughly speaking, and now let's try to put this together. Plug and chug. So this is going to be my final velocity. So 60 minus 0 over 6. So which would then be 60 divided by 6, which is going to give me an acceleration of 10 meters per second squared. Okay, and I have my answer here. Not too shabby. So what that means then in this case, for every second that passed, this car increased 10 meters per second. Okay, I'll say that again in a different way. This car increased its velocity by 10 meters per second every single second. Okay, so that's what happened there. And that's the answer for this guy right here, 10 meters per second squared. Okay, so let's try number 2. So I'll read it out. Make sure you complete this on your own. A cheetah is running at a rate of 31.3 meters per second to catch its dinner, but runs out of energy and eventually comes to a stop after 32 seconds. Calculate the acceleration. Ooh, this one is an interesting one. So we're starting. Oh, sorry. I almost solved it. Pause the video here. And try this on your own and then come back and see what you get. See if you got it right. Okay. So we're starting here. Let me check the time. Of course. We're starting here where we start off with a rate of 31.3 meters per second. Okay, so that means that our initial velocity is 31.3 meters per second. So that's our initial. And it tries to catch its dinner, and then it eventually comes to a stop. So that means that we started at this rate, this 31.3, and then eventually it goes to rest. It then stops. It's no longer moving. Its velocity is 0. And it does it in 32 seconds. So it says our time is 32 seconds. And we're asked to calculate the acceleration. Okay. So my formula, again, is still just the acceleration is equal to final velocity minus the initial velocity over time. So I'm going to plug all that in. So when I plug that in, it's going to be, this time, it's going to be 0 minus 31.3. And I just remembered that I forgot to include the direction in my answer for acceleration in the first one. So there's going to be a direction on this one, 100%. So it's going to be 0 and 0, not 31.3 minus 0. It's 0 because 0 is our final velocity minus our initial velocity, which is 31.3, divided by 32. And when I put that into my calculator, so that's going to be a negative 31.3 divided by 32, which is going to give me an acceleration of roughly negative 0.9, let's say, oh my goodness, come on, man, 0.98. okay, meters per second squared. Okay, and here, so let me clear this out. So my answer here is going to be 0.98 meters per second squared. It's a negative, but I'm not done yet because I need to show that this is a direction. So we're going to say that, let's just say for the sake of argument, the cheetah initially is running this way. But because we're moving in this direction, the cheetah is moving in this direction, but then comes to a stop, the acceleration is not in the same direction as the movement. Okay, so we'd say here that because it's opposite, and that's clear because now we know that because mathematically it shows that the acceleration is negative. Because the acceleration is negative, that means it's in the opposite direction of our movement. So that we'll write this, is that the acceleration is 0.98 meters per second squared in this direction. Okay. So this right here is the initial direction that the cheetah was moving. This is the direction over here. This is the direction that the cheetah was accelerating in. It was opposite of the motion of the cheetah. Okay. Okay. Let's take a look at number 3. So read it, and then you need to complete it on your own. So Upton Chuck is riding the giant drop at Great America. If Upton free falls for 2.60 seconds, what will be his final velocity? So just so you know, free falling is to say that he's accelerating in the downward direction, acceleration due to gravity, at a rate of 9.8 meters per second squared. So you're given acceleration, you're given time, and you're given final velocity. And you're given initial velocity, and you need to find final velocity. So go ahead, try this on your own, pause the video, and then come back to see what you get. Okay, so to lay out our variables here. So looks like we were given time. This dude has fallen for 2.60 seconds. Okay, we know that he's starting from rest because we know that this drop thing is, we know what it is. We're starting from rest, so it's 0 meters per second. And then we're given acceleration, which in this case is going to be, oh my goodness, come on. Jeez. 9.8 meters per second squared. And we're tasked to find final velocity. Okay, so I'm going to look at my notes, and I'm going to see that in order to find final velocity, I need to use that final velocity equation. Oh my goodness. Oh my goodness. Which is going to be acceleration. This is, come on. Look, a lot of gunk just gets built up on my stylus here. Acceleration multiplied by time plus the initial velocity. Now, what's great though is that we really don't care about the initial velocity in this scenario because the initial velocity is 0, so we could just ignore them. So it's really just acceleration times time, okay? So that would be then final velocity is equal to 9.8 multiplied by 2.60. So we'll put that in our calculators. And what we should get for acceleration here, or sorry, for final velocity, we should get that final velocity in this case.
Connor Stone, Keegan Stone, please come to the office. Connor Stone, Keegan Stone, please come to the office.
Is going to be 25.5 meters per second. And in this case, we're going to say, we still need to add direction in the downward direction because he's falling. So this is what we just solved here, is to say that if this dude is going to accelerate 9.8 meters per second every single second, and he's falling for 2.6 seconds, starting from rest, his final velocity should be 25.5 meters per second, okay, in the downward direction. So pretty much this is the, sorry for the bell, this is the rate in which he'll end, at which he'll then end the little drop here. Number 4, so a sled begins at the top of a hill at rest, accelerates to a speed of 3.5 meters per second. If it takes the sled 8 seconds to reach the bottom of the hill, what is acceleration? So let's see here. So pause the video and then try this on your own, come back, and then see if you got it right. Okay. So it looks like here the sled begins at the top of the hill with initial velocity. So that means our initial velocity here is 0 meters per second. We have a final velocity of 3.5 meters per second. This all happens in 8 seconds. Okay, so 8 seconds. We got here, begins at rest, and we're asked to find acceleration. Okay, I'm going to write out my acceleration equation here, which is just acceleration is equal to final velocity minus initial velocity over time. Okay, and now I'm going to plug all that in. So my final velocity is 3.5. My initial is 0, and I did this all in 8 seconds. So then my acceleration here, 3.5 divided by 8. So my acceleration here is simply just 0.4375 meters per second squared. We'll just say in this direction. Why not? I know it's down. It's supposed to be downhill. We're going to just say in that direction, just to keep things simple. So what you should have found is the acceleration here should have been measured at 0.4375 meters per second squared.
Mrs. Grief, please come to the office.
Okay, sorry about all the interruptions here, guys. Okay. And then let's take a look at number 5. Okay, so a car starts from rest and accelerates uniformly over the time of 5.21 seconds for a distance of 110 meters. Determine the acceleration of the car. So what you're going to do here, pause the video and then come back, see if you got the problem correctly. Okay. Okay. So car starts from rest, so we're starting from rest here. So my initial velocity, 0 meters per second, accelerates uniformly over a time of 5.21 seconds. Okay, so that means here that our time, and this is the tricky one, 5.21 seconds, and it's for a distance of 110 meters. Oh, that's weird. We've got displacement, 110 meters. Determine the acceleration of the car. So we have 2 unknowns here. We have both acceleration as the unknown, and we also have final velocity as the unknown. And we need to figure out final velocity before we can figure out what we need to figure out final velocity before we can figure out the acceleration. Okay, I had to pause the video for a while, and I'm trying to remember where I left off. I'm just going to do this. I'm going to reread this. Sorry if I already read this out, but I'm going to reread this. And then I'll have you pause it and complete this on your own. Oh, actually, now I remember where we started with this. Okay, now this one's tricky, and arguably now I'm looking at it, I've had a chance to think about this for a second. I did realize that this is going to be this is something that we don't get into. Look at check your understanding, number 5. Yeah, this is something we don't get into, and we're not going to get into because it is fairly complicated. It just relies upon you guys having a different number of different equations, and they're called the kinematic equations. Sorry about the bell, and you'll probably hear another one while I'm ending this video. But if you're curious about this problem, look up kinematic equations or the 5 kinematic equations and see if you can solve this. Because again, just to reiterate what you have and what you don't have. Okay, you've got initial velocity and it's 0. You have time, and time is 5.21 seconds. Okay. You have distance. Really, it's displacement, actually. You have displacement, which is 110 meters. And you're asked to not only find the acceleration, but you have to find the final velocity. Okay. And you also have to find acceleration. Now, again, there's kinematic equations where you first, or that you use in order to find this first. And real quick, I'll walk you through it. So again, this is not something you need to know for my class. So if you're watching this right now and if you're not interested in watching, seeing what I'm about to do, you can go ahead, turn off the video. You're good to go. I'll see you on the next in-class day. But if you're curious on how you would find both the final velocity and also the acceleration, stay on just for a bit longer and I'll show you how to do that. Okay. So let's go through this. So what you have to do here, and again, this is something we haven't gone into, you have to find what's called or have to use an equation that's just the average velocity. Okay, something that has been mentioned before but not used. So all the average velocity is, this is how we denote it. It's VAV, and all it's equal to is the final velocity plus the initial velocity, and it's divided by 2. Okay, so we can use, and not only that, average velocity is technically also just found this way, that it's just simple displacement over time. That's pretty much what we've been solving for. So what we do is we just more or less smack these two together. So then it becomes final velocity plus initial velocity, divided by 2 is equal to the displacement divided by time. So it turns into that. And then we just solve for the final velocity. So, which is decently easy because this guy we can ignore because it's 0. To get rid of the 2, we multiply 2 on both sides. So then it becomes VF is equal to displacement divided by time times 2 is what it turns into. Okay. Okay, that's what that turns into. Oops, didn't want to erase that. And so once we do that, and again, why is it that we have to use the average acceleration? We've got to use average acceleration here because technically speaking, okay, if we're technically speaking, that's just it's an equation that has final velocity in it. It has final velocity in it, and we can use that to find what we're looking for here. Okay, that's really all it's used for. So then I'll just rewrite it over here, but I'm going to plug everything in. So then it would be 110 divided by time, which is 5.21, and then it's times 2. And what you would get for your final velocity then, here, let me quick pop that into my calculator, 110 divided by 5.21. What you'll get here is 21.1 meters per second. Okay. Okay. So that is our final velocity here. So we've got that. So 21.1. So now we've got final velocity. It's 21.1 meters per second. We have initial velocity, which is 0 meters per second. We have time, which is 5.21. Yikes. And then we need to find out what the acceleration is. We don't know acceleration here. And here I'm going to just double check here. Oh, here are my kinematic equations. Yeah. Yeah. So, okay. So then now that we've got final velocity, we've got to find out the acceleration, which acceleration is just final velocity minus initial velocity divided by time, okay? Which is then going to turn into just 21, come on, 21.1 divided by 5.21. Then we'll have acceleration here. Because remember, initial velocity is 0, so we just ignore it. That's 21.1 divided by 5.21. And then that's going to give us an acceleration here of 4.05 meters per second squared. And we'll say forward because it is speeding up. Okay. So again, so this problem, we don't need to know from my class. I've kind of slipped in there and I kind of forgot it existed, to be honest. We're not going to use that for this, use this kind of problem for this class. So don't worry about it. But if you stuck around to watch this, good on you. That's really cool. And hopefully, you know, this is what we do in physics. So keep that in mind that when you become a junior or senior and you really want to take physics, you know, talk to me. Talk to Ms. Doherty, talk to Mrs. Norton, whoever it is, in order to, see what it would be like, or ask around to see what it'd be like to be in physics, because this is what we do. Okay, so and it's a really cool little thing where it's basically a puzzle. It's a mathematical puzzle. That's all it is, which I know is hard to kind of think about when you're in high school, because I definitely didn't think of it in that way when I was in high school. But at the same time, I don't ever remember having teachers like just say, yeah, it's like a puzzle. You know, so yeah, that's really all it is. You know, you're using what you have, what you don't have, and then you use equations and formulae, and you know, try to piece the puzzle together. It's really all you're doing. So anyway, so guys, thank you for sticking to the end of this video. Thank you for sticking around. If you have any questions, make sure